Welcome back to the stats series. You might have noticed the background has changed color here. This is going to be the first in the statistics series where we talk about how to practically solve problems as opposed to the theory behind them. This is especially important in statistics because a lot of the theory gives rise to different functions that are in practice very challenging to compute by hand, and often in the field we will delegate these problems to computers. So in this case, we're going to be dealing with graphing calculators, or R, the coding language most popular among statisticians. And I'm going to work through a couple binomial distribution problems just to show you how you would handle those types of problems in academia, but also in real life. So let's get into it. So first of all, if you haven't watched the theory video on the binomial distribution, I highly recommend you check that out first. But maybe you're in university or you're in an AP class and you just want to see some examples of how to solve these problems, and you've already taken a look at the theory behind it. In that situation, I'll just mention that the way that you are going to utilize the cumulative distribution functions, if you're using a graphing calculator, you will just push second vars. That will pull up the distribution section on your calculator. That has a couple handy statistical functions, but the ones of note are almost at the bottom. Going to be these Binomial CDF functions, which is going to give you the cumulative distribution function, and the Binomial PDF, which is going to give you the probability mass function for the binomial distribution. If you are using R, on the other hand, like me, then your CDF is going to somewhat counterintuitively correspond to P binomial, and then you're going to input the observed number, the number of trials, and the probability. And if you are after the probability mass function, you're going to use the D binomial function with the same exact inputs. All right, so now that we have that information, let's actually get into solving some of these problems. And of course, I should mention before we actually get started here, if you want to get the most out of a video like this, any video, on mathematics or science for that matter, I highly recommend pausing the video at each one of these questions and trying to work your way through it on your own. That being said, let's actually get started. All right, so our first problem here says a programmer is trying to develop a random number generator, and she wants to implement a coin flip function in order to test her program. Her first attempt resulted in 68 heads and 32 tails, so that doesn't seem great. But what is the probability of getting more than 60 heads, assuming that the program is working perfectly? That's the first part of our problem here. So let's negotiate that. I'll write it off to the side here. Part A. What's the probability of getting more than 60 heads? Well, this would be 1 minus, I'm going to use binomial CDF. I'll use the notation on the graphing calculator for this because I think it's a little closer to what you might expect when you're thinking of CDF versus PMF. Binomial CDF is just the cumulative distribution function, versus in R, we're talking about P binomial, which might be confusing. So I'm going to use this notation when I'm writing this out. But we're asked here, what is the probability of getting more than 60 heads? So we want to do 1, which would be the total probability if you add up all of the possible outcomes. And then we want to subtract the cumulative probability up to 60. And if we subtract off all of those possibilities, we'll be left with everything that's remaining. And so if we do 1 minus the cumulative distribution function for, let's see here, we're doing 100 trials, and we want to have an outcome here of 60, and their probability should be 50%. And so what's the probability of getting more than 60 would be 1 minus this right here. This would be the cumulative distribution function evaluated at 60 for 100 trials and a probability of 50%. And if you plug this into a calculator or R, this is the exact equivalent way of representing this in R, you would get 0.176, so a little bit less than 2%, but it'd be a 1.76% chance of this happening. So in part B here, we're asked, given this information, is the program working as intended? Probably not. I mean, if we have this outcome and there's only a 1.76% chance of this happening, we could be pretty confident in assuming that the program is not working as intended. And now in part C, we're asked, the programmer increases the number of trials to 1,000 and finds that she gets 710 heads and 290 tails. Given this information, she determines that her program is functional, but is effectively just implementing a weighted coin with a 70% chance of landing on heads instead of the desired 50%. So if this is true, would the results of her experiment be within one standard deviation of the expected outcome? This is a two-part question here. So what is the expected outcome? The expected outcome is just the mean of this binomial distribution, which is just the number of trials multiplied by the probability. So this is just going to be 1,000 multiplied by 0.7. And so that's just going to be 700. This is what we would expect. And what about our standard deviation? Well, we have an equation for our variance. This is just going to be equal to 1,000 trials multiplied by our 70% probability. And then we would need to multiply by the complement of this, so that's going to be 0.3. And this evaluates to 210. But we have to remember that this is the variance. And so if we want the standard deviation, we have to take the square root of this. So this is going to be the square root of 210. And that's just going to be, looks like about 14.491. 14.491. And so when we're asked here, we're asked, is 710 heads the result of her experiment? Is that within one standard deviation of the expected outcome? Well, one standard deviation away from this expected outcome would be 714. That would be within one standard deviation. You can't have 714.491 heads. You can only have a whole number outcomes for heads or tails. And so 714 would be the closest integer value that's going to be within one standard deviation of the mean here, which is 700. And her outcome of 710 certainly is within one standard deviation there because it's less than this 714 value. So this is going to be less than one standard deviation away from the expected mean. We've got a second example here. It says, on a whim, you decide to roll a die and start recording the outcomes of each dice roll. In particular, you are recording whether or not the die lands on a 1 or not. You decide to model your experiment as a binomial distribution, and you come up with a standard deviation of 1.5366. The first part of this question is asking us how many times are you rolling the die. So just to go over a little bit of information here, we're recording whether or not the die lands on a 1 or not. And so our probability here is going to be 1/6. And we get a standard deviation here for our binomial distribution of 1.5366. And that is all the information we have in this problem. And so let's go ahead and start this off. It says in the first part, we're asked, how many times are we rolling the die? Well, the way that we could go about solving this is we have an equation for the variance, and we have given the standard deviation. The standard deviation squared is going to give us our variance. And so if you square this 1.5366, if we square this, we will get 2.361. So this is going to be our variance. And we know that our variance is just the number of trials multiplied by the probability and times the complement. And so we can actually solve this equation for the number of trials. If we do if we just divide by this probability here, we get 2.361 over 1/6 times 5/6. And if you plug this into your calculator, you'll get something like 16.9992, it looks like. But given the fact that we can only do a whole number amounts of trials, we can reasonably conclude that probably what happened here is the standard deviation was rounded off. And so when we squared it, we got a variance that was rounded. And so really what's happening is the amount of trials here was 17. It has to be an integer value. It's very close to 17, so that's probably where they started. And if you go with 17 trials and a probability of 1/6, you could compute the standard deviation, and when you round it off, you will get something like this. And so we are done with part A. And now part B is asking us, what is the expected number of times you will roll a 1? So this is very simple. This is just asking us for the mean of the binomial distribution, and the expected number of times that we'll roll a 1 here is just going to be our probability multiplied by the number of trials. And so if we carry out that operation, we'll get the number of trials multiplied by the probability. It's going to be 17 times 1/6. And we are going to calculate, looks like 2.833. Now I want to point out here that we are actually done here for part B. This is going to be our expected value. We're going to say it's 2.833. And you might have the question in your head, well, why don't we have to round our expected value or our mean of this binomial distribution to a whole integer? Why is it okay to leave this as a decimal, whereas our number of trials has to be a whole number? And the answer to this question is that as statisticians, our goal here is to make useful statements about the world around us. And so in this case, we want to make a useful statement about the expected value of this experiment. And if we want to make a statement about the expected value of the experiment, you can imagine what we want to do is we want to take into account both the value associated with every possible outcome of the experiment, as well as the probability associated with that outcome. And so essentially all we're doing is we're applying this formula for the mean of a distribution. Here we're starting at 0, which is one of the possible outcomes, and we go up to 17. This represents all the possible outcomes. You can have 0, 1, 2, all the way up to 17 possible outcomes for the number of ones that you roll out of 17 dice rolls. And then we want to take the value of that outcome, and we want to multiply it by the probability of that outcome, which is given by this probability mass function for the binomial distribution, the binom PDF, evaluated at, we have 17 trials, 1/6 probability success for each trial, and here we're evaluating this at I for every possible outcome. And when you sum up all of these, what you're doing is you're taking into account every possible outcome and its associated probability by taking the product of those two variables. And when you do that, you get the expected value of the experiment. Now, some of these probabilities here are going to be very small numbers. You can try this yourself. Try putting in 5, 6, 7 for the I in this equation. You'll find that you're going to get a very small decimal number, and even when you multiply it by 5, 6, 7 respectively, the contribution to this average is actually very small. And you can imagine that that makes sense. What's the probability of rolling 7 ones out of 17 dice rolls? It's not very high, and so you don't want to lift the average so substantially. And so by taking into account both the value of the outcome, every possible outcome of the experiment, as well as its associated probability, you do get these very nuanced small decimal values for many of the possible outcomes. But we don't want to just ignore those by rounding off to the nearest integer. That would distort our analysis of this experiment pretty heavily. And so generally, when we're reporting things like mean or standard deviation, we will report it with the decimal values, with the understanding that it's not possible to roll 2.833 ones in this experiment. And more to the fact that this is open to interpretation. So it's more likely that the most possible, or the most likely occurrence here is going to be that you roll 3 ones, for example. But there's also going to be a pretty significant probability that you roll 2, or maybe 4, something like that. And so we're supposed to recognize that it's not possible to roll 2.833, but we can interpret this, and we're not distorting the data by rounding it so heavily. And so that's the reason why we don't round this. And you can imagine, you've probably seen this before. For example, infant mortality in the United States is 5.6 deaths per 1,000 people. And so you can't have 0.6 of a person die. These are represented in this way to capture the actual rate of infant mortality to the highest degree of accuracy possible. And we don't want to distort this by just rounding it up to 6, because that would be a pretty significant change in the data. So now let's do part C here. Part C asks us, how many ones would you have to roll in order to have an outcome 2 standard deviations above what is expected? And so let's take our expected value here of 2.833, and let's add 2 times our standard deviation, which is actually given to us in the problem. And so it's going to be 2 times 1.5366. And what you'll get if you calculate this out is it's like 5.91, essentially. And now in this case, we're asked how many ones would you have to roll in order to have an outcome that is 2 standard deviations above what is expected. And in this case, you can't roll 5.91 once. And so in this case, we do have to round up. And now, incidentally, rounding this number would go to 6. But let's say, hypothetically, for the sake of argument, that we got, when we carried out this operation, we got 5.41. In this case, we still do need to round up because we're asked how many ones do we have to roll to have an outcome that is 2 standard deviations above what's expected. And so we need to make sure that our result of the experiment is actually above 2 standard deviations of the mean. And the only way to ensure that is to round up, regardless of what the actual integer or decimal value here is. We need to round this result up to ensure that our actual outcome is 2 standard deviations above the mean. I actually think this is very important, so I added another problem here. How many ones would you have to roll to have an outcome 3 standard deviations above the expected value? Here the procedure is going to be almost the same. We're going to take our expected value and add 3 times the standard deviation here, 0.5366. But when you carry this out, you're going to get 7.4428, looks like. And so here, in this case, if you rolled 7 ones, that would be less than the 7.4428 value, and so it would be less than 3 standard deviations above the expected value. This is the precise answer to our question as to how many how many ones would you have to roll to have an outcome that's 3 standard deviations above the mean. This is the answer we want, but we can only roll whole number. There's only whole number outcomes to that question. You can only roll whole number amounts of ones on a dice. You can't roll 7.4428 ones. And so if you were to roll 7, the outcome would be less than 3 standard deviations above the expected value, and so that would not be right. Even though our inclination here is to round this number down, in this case we have to round this number up, and so the correct answer here is going to be 8 rolls. You would have to roll 8 ones for your outcome to be above 3 standard deviations above the mean. And just as a final little point here, I actually graphed this probability distribution, and you can start to see now that we have 2 values here. We have the point on this graph that would be within 2 standard deviations of the mean is going to be 6. It's going to be this outcome right here. And so it looks like this is going to be 2 standard deviations within the mean, which seems to be resting right about here. That's 2 standard deviations. And then this 3rd standard deviation will take us all the way out to 8. So here's 6, 7, and it looks like 8 right about here. So that's going to be 3 standard deviations above the mean. So anything out here is going to be more than 3 standard deviations above the mean, including this 8 here. Right, this is the last question I got here for this video, and this is going to start to sort of introduce a couple new topics here, even though we are perfectly capable of solving this problem. It says a vehicle manufacturer claims that 98% of their airbags deploy safely and effectively. In a compliance study, an independent group of statisticians observed that out of 100 instances of accidents involving the manufacturer's vehicles, the airbags were deployed properly 91 times. So the first part of this question says, what is the probability of this occurring? And so this is just going to be that probability mass function, or that binomial PDF. Here we have 100 trials. And we have a probability here of, let's say, 98%. There's a 98% chance of the airbags deploying properly, and it looks like they were deployed properly 91 times. Now, I want to point out this is exactly the same as saying the binomial PDF, or that probability mass function, out of 100 trials with a probability of 0.02, taking into account the probability of those airbags deploying improperly, and doing 9 trials where that happened, because that is the exact same way to represent the results of this experiment. And if you plug both of these formulas into your calculator or R, whatever you're using, you'll get the same outcome, which it looks to be 0.000155. And so that's going to be our answer for part A. Now, one thing I want to point out here is that although this probability is very, very low, we have a lot of trials here, and this probability mass function is only taking into account the precise, the exact situation in which 91 airbags deploy properly and 9 airbags deploy improperly. And so this number is going to be small really no matter what. If you do the probability mass function, here, the Binomial PDF, for the actual expected value of this distribution, so let's do a 2% chance in 2 airbags deploying correctly, that's going to be 2% multiplied by 100 possible, or 100 trials, it's going to give you 2. So this is our expected value. If you carry this out, this is still only going to give us 27.3% chance, a 27.3% chance of this happening. And although that is absolutely orders of magnitude higher than what we're observing here, this is still a pretty small chance of happening. And so you can imagine that as a natural consequence of this, as we're looking at these studies that involve more and more and more observations or more and more data, instead of looking at precise actual outcomes, we might be more interested in a range of outcomes. Maybe within, I don't know, if you look at the next part of this question, for example, what is the probability that less than 5 airbags deploy improperly given the manufacturer's claim? This might be a much more useful question to answer in the real world as you're dealing with more and more data points than these precise, exact answers, like what's the probability of 3 airbags deploying improperly? That's always going to be low, even in the most likely event, especially as you get more and more data. So I just wanted to emphasize that here. And that's actually a good segue into our next question here. What is the probability that less than 5 airbags deploy improperly here, given the manufacturer's claim? There's 2 ways to work this, and I recommend being very careful when you're reading these problems because we're asked about less than 5 airbags, strictly less than. So the situation in which 5 airbags deploy is not going to be considered into this probability. And we're also asked about the airbags deploying improperly, whereas in the question, we're given information about the proportion of airbags that do deploy properly. And so we have to make sure that we're keeping all of that information in mind. I think the easier way to work this problem is to recognize that if 98% of airbags are deploying properly and airbags can only deploy properly or improperly, then the probability of an airbag deploying improperly is going to be 2%. And if we want the probability of less than 5 airbags deploying improperly, then we want the cumulative distribution function here with 100 trials and a probability of 0.02. And we want to evaluate this at 4, because if we were to evaluate this at 5, we would be including that situation in which 5 airbags deploy improperly, and we don't want to do this. This question here is asking about the probability of strictly less than 5 airbags deploying improperly. So this is going to be the correct answer here, evaluating this function. But the other way to do this is to use the information that's given in the question directly. It's just a little bit more complicated because it involves recognizing that less than 5 airbags deploying improperly is the same as more than 95 airbags deploying properly. And so you have to make sure that you keep all of those straight. And so you want to take the complement here, so we do 1 minus the cumulative distribution function. And then here we have 100 trials. And then in this case, we're going to use a 98% chance probability of the airbag deploying properly. And now what's going to be the last value in this function here? Now, once again, here we have to be very careful because if we're going to approach the problem this way, we want to take into account all of the possible outcomes. So that's represented by this 1 here. If you add up all the possible outcomes here, get a value of 1. And we want to subtract all of the outcomes in which less than 95 of the airbags deploy properly. If we subtract off all of those events, we're going to be left with the outcomes in which more than 95 of the airbags deploy properly. And if more than 95 of the airbags are deploying properly, then less than 95 or less than 5 airbags will be deploying improperly. So in this case, we do need to include this fifth airbag, so to speak. In this case, it's going to be the 95th airbag. But if you don't like being that, you have to keep track of so many different details, and I think this is an instance where it's easier just to take the information in the question, modify it just a little bit so that it makes answering the question a little bit easier. Taking that 98%, converting it to 2%, I think is a lot easier than having to keep track of, okay, we're dealing with strictly less than, so we need to flip it, and then it's going to be strictly more than, and so we do need to include it. If it's strictly less than, we don't need to include it. So you just need to be very careful with those details, and I think in this case, this is just a much easier way to deal with the problem. But if you plug both of those into your calculator, you will get a probability of about 95% here. So the last part of this question here is asking us, based on the results of the researcher's study, what can be said about the manufacturer's claim? Well, the manufacturers claim that 98% of their airbags are deploying effectively and safely, would lead us to the conclusion that 95% of the time, less than 5 airbags should deploy improperly. And in the study conducted by these statisticians, we had 9 airbags deploying improperly, which is almost double what you could say would happen 95% of the time. And so I hope it's a little bit clear here that the odds of the manufacturer's claim being true, given the results of this study, seem dubious at best. It doesn't seem to be very likely that the results of that, or that the statement being made here by the manufacturer is actually a true statement based on the results of this study. And as we move forward into this course, we're going to talk about confidence intervals and hypothesis testing, and we're going to actually put mathematical statements behind this and quantify this sort of intuition that we're having here that this might not be true. So I hope that sounds interesting. I hope this was a entertaining video. If it wasn't entertaining, I hope it was useful. Thank you all for watching.